All right, let's get started. So, a couple things about synchronous generators. And the biggest thing, or the biggest issue with synchronous generators is they have to operate at synchronous speed, right? They have to operate 3,600 RPM, 1,800 RPM when they're connected to 60 hertz. And the thing is that the only way the grid today works is when you have lots and lots of generators all putting energy into the grid. So all these generators are interconnected. And so what ends up happening is if one generator, its prime mover is what's dictating the speed of operation. If that prime mover is 3600.2 hertz, and the one next to it is 3600.1 hertz, then they're going to be fighting each other, right? So operating generators synchronously or in a mode that basically it's called droop mode, but now they're starting to change it to grid following mode. It makes it more difficult. So we'll talk about more and more of that as we get into the parallel operation of these synchronous generators. But ultimately, what does it do? It provides a lot better reliability. Maine has a peak demand of 3 gigawatts. And conceptually, you could have a generator that's rated for 3 gigawatts. The problem is what happens if that generator fails and the entire state of Maine is out of service. So it's generally better to have lots of smaller generators, and then you can have some spinning reserve. So let's just say that load right now in Maine is 3 gigawatts. You could have generation that has an equivalent nameplate rating of 3.2 gigawatts, and some of those generators are not operating at full output, right? Because they're capable of 3.2, but they're only exporting 3. So the concept is you have what's called spinning reserve. These generators are actually up and operating, and they have the ability to very rapidly increase their power output, but they don't need to output more power. It's the same idea as if you're driving your car down the road and your foot is on the pedal halfway, and then you go to a hill and then you floor it or whatever you need to do. So your car provides that same spinning reserve where you have more availability out of the unit, but you don't necessarily need it, okay? So that's how the grid often operates. Some plants operate at full capacity, like nuclear power plants. They run, when they're running, they're almost always at 100% output power. And the reason being is because once you're up and running a nuclear power plant, the fuel costs are very low as compared to, all the other stuff at a nuclear power plant. So they really make their money when they're outputting maximum power. The other challenge is nuclear power plants, they can't ramp up and down in power readily. So their design run at full output power or basically shut down. That's kind of the two modes that they operate best on. That's for commercial nuclear power plants in the United States. If you're on a naval submarine or if you're on an aircraft carrier, everybody hopefully knows that those are nuclear powered. Anybody guess as to why a nuclear submarine is powered with nuclear?
Probably fuel storage.
Lighter? Don't need fuel. What's the biggest thing about
It's not silent.
not silent, reliable,
There's no emissions.
no emissions? If you have
Not explosive.
not explosive, it can be.
It can be cooled very easily.
Well, you're underwater, so you can do anything. But what does a reciprocating engine need? Fuel, air. You're underwater. Where do you get the air from? A what? A what? Doesn't want to say. You don't have air that's readily available. So older submarines, they were diesel powered, diesel fired, and they would have a snorkel. So they would actually run a tether that was basically a big pipe, and they would run it up, and they would actually have the ability to get oxygen, just like fish do, right? There's oxygen in the water, just like fish. They would actually get oxygen out of the water, and then that's how they would get their oxygen to put into their diesel engines to actually burn. That's part of the combustion process. You need oxygen for that. In a nuclear reactor, you're splitting atoms. As you split atoms, you create heat. That's your energy source that you need. So in a nuclear submarine, it makes perfect sense to be nuclear powered because you don't need any oxygen. You can run for days and days and days. You actually still need oxygen because there are humans on submarines, right? So you still need to get air, oxygen, and dump out the carbon dioxide that's in the submarine. So you do actually still have to have air, but in terms of the major source of air needed in a submarine, it's just for human consumption. Not like in old diesel submarines. And you can tell navies that are limited in terms of their stealth technologies or speed is the submarines just can't go that fast if you're pulling diesel. The other thing about submarines, and again, I'm getting off topic a little bit, but submarines, they have to get fuel if they have diesel. A nuclear submarine, what do they have to go up for? Food for the humans, that's it. The only reason why they need to surface, they could go down for years as long as the maintenance is done. But you could have a submarine that could go down underwater for years if you didn't have to feed the people that are on there. So that's the longest deployment thing, is how long can it go before you run out of food? There's also a lot of, and if it's really fascinating, if you have a chance to look at it, there's a lot of psychology. I mean, how depressing is it? You're in a metal tube for months on end. It also starts to affect your psyche. So it actually affects your mental health, not seeing the sun and all that stuff. So deployments can be 6 months, but they're not deployed undersea for 6 months. They have to port at some point to get fuel, food, and then also to get a little bit of, nice weather for the soldiers on board. But on a ship, on these submarines, they also have what are called ship service turbine generators. Those are steam fired, and they actually produce the 60 hertz AC that the ship uses. It could be any frequency you want, because once you're out away from port, you can produce whatever voltage you need. But in the United States, all the submarines are 60 hertz, because when they go on the shore, it's always best if you can shut your reactor down or run it at very low power levels, and you can get ship service power, which is on board. I mean, which is what you get from the port. And so you'll see a big wire that gets plugged in, and that provides all the power for the ship that they need. So they can shut down the reactors, they can do maintenance. They don't have nearly as much staff to maintain the reactors as they do when they're running at full power. So you'll have at least 2 ship service turbine generators, SSTGs, and they produce 60 hertz. Those oftentimes run in parallel with each other to make sure that they're sharing the load, so that if one fails, they can switch over really quickly. Because if you're underwater and you lose power, there are backups with batteries and all that stuff, but you don't have a long period of time before you have to surface and gimp home. So if you lose all your AC power, you switch to DC so you can get your reactor to a certain point, but it's usually 8 hours and you can get out of harm's way. There's actually a small DC motor that can drive the propeller to get you a few miles. I don't know how far, but you can get to hopefully a safer place. But again, that doesn't happen all that often. Yes, Avery.
They wouldn't do a parallel operation with the.
No, they could, because if it's not the price, right? This is military, so they can spend what they need. It's more along the lines of what is the reliability demand? And then the other thing is the space. So how much space do you have? So you can run as many transformers as you need, unless it doesn't enhance the reliability, or you don't have the space for it. So most of the time, it's like a commercial nuclear power plant. You have sort of 2 sides, where you have one SSTG that can do all the AC loads for the submarine. And then they have another SSTG that can do all the loads for the submarine, and they're not interconnected. So if something happens on B, it doesn't take down A. Or if something happens on A, it doesn't take down B. They're independent from each other. And they're routed physically. So if you have a fire, there's ways of routing things. There's a lot of design in terms of making sure the reliability is that way. Same thing at a commercial nuclear power plant. They actually have 3 trains. They have 2 official ones, and then the third one that's kind of a backup one. But all those have to be physically isolated. There's a bunch of rules for that. Okay. So we're going to do parallel operation. Here's how you do parallel operation. And we can actually do this in lab when we have a chance to get to it. We'll do this lab where we will synchronize 2 generators, or we'll synchronize a generator to the grid. This one is showing it to the load, but you can certainly synchronize to a grid. And essentially, all 3 phases have to have approximately the same voltage and approximately the same frequency. And so when you actually want to synchronize 2 generators together, you have a leader. So let's say generator 1 is a leader one that's running at 60 hertz. It's rated for 60 hertz. And then you want to switch generator 2 on to help out with the load. So the way that you do that is you monitor, usually at least it's only one phase. You're actually monitoring the phase angle of one phase, and you don't do it with an oscilloscope. You do it with something called a synchroscope, and you're monitoring that one phase, and you can tell when the two are in phase with each other when there's no difference, there's no voltage difference. So they normally will monitor that with a light. So if the light is dark, there's no voltage difference. That means they're in phase with each other. When the light is bright, don't close in there because you're 180 degrees out of phase and you could cause a fault. The other thing you want to do is you want to make sure your generator frequency is pretty close to what the existing one is. And normally you want this generator frequency to be slightly higher than the other one. Because if you're right at the same speed and your light is bright, they're always spinning at the same speed. So they're never going to, the light's never going to get dim. So you have one spinning faster a little bit. And that means that the light starts off bright and then it gets darker and darker and darker until it turns on, and then you can sync in. And the only other thing you want to make sure of is the voltages are about the same. But normally, again, that oncoming generator, you want its voltage to be slightly higher because you don't want to monkey around too much with the excitation. That's kind of the synchronization process. Yes, sir.
What would happen to the load if, like generator 2 was generator 1?
It depends on the relative size of the generator. So if generator 1 is much larger than generator 2, generator 2 is going to look like a load for a period of time, and it's going to bring itself in line with generator 1. If generator 2 is much bigger, then the opposite happens. So it's whatever the bigger one is what dictates what happens. Fortunately, when we connect to the grid has thousands of generators. So your one generator, even if you're a nuclear power plant, if you try to monkey with the grid, you're not going to have much success. So if you tried to close a 1500 MVA generator out of phase with the system, it will force that generator to get up to speed to whatever the grid system is. The generator may not like it, and you probably ruin the generator, or you may have ruined the generator, but you can certainly try that. So here's our case, right? Where we have many generators all interconnected. They're all running in parallel with each other, right? They're not in series because this is only showing you a single phase. So this generator here is essentially in parallel with that generator. You have a small transmission line between them. So they're not truly in parallel, but they're close enough to be in parallel so that the voltages would be the same. And then here's our load. We characterize it here. We can redraw that onto this common bus. We can see that we have this common bus over here. And then we can see that we have these different units that are represented with this synchronous reactance. So we can come up with this concept of an equivalent circuit. These are the individual generators. This is the big generator. So what we often do is say that this bus right here is an immovable object. That's what those squiggle lines coming off the side mean. And it's essentially, another way to say that from an electrical standpoint is it's an infinite bus. It can provide or absorb infinite amount of energy to maintain the voltage at the bus as well as the frequency. There's nothing you can do to change that. That's how we do it. Typically in an educational environment, but if you're out in industry, there is the possibility of moving things a little bit. Like if you're that 1500 MVA generator and you were constantly trying to monkey with the voltage and you were, tweaking as much as you can or trying to change the frequency, when you're that big, you do have the ability to move things a little bit, but usually you get kicked offline by the transmission owner in that area because they can't tolerate that. They can't deal with that. So we'll use this concept of an infinite bus as an immovable object, and we'll use it a lot in the follow-on class to this class. So the only analogy that I would tell you about an infinite bus is the concept of a water hose filling a tank. So you have a garden hose and you turn it on and the water is, splaying out a little bit. You're trying to fill a 5-gallon bucket. That takes, I don't know, whatever it takes. But instead of that garden hose filling a 5-gallon bucket, what if you're filling a 10,000-gallon tank? And that tank also has other lines coming in and out of it that are maintaining the tank level. So no matter how much you adjust your hose, max or min, that voltage never changes. Okay? Or the level that will change it. See, I said voltage, but I really meant to say level because that's what the proportional equivalent is. So in many power systems, you have an infinite bus. We oftentimes think of our utility connection, at least from a loads perspective, as an infinite bus. It can provide or absorb as much power as necessary. But in reality, you do see some changes, especially at the distribution level. You can see quite a bit of fluctuations. If you were to go to Orrington, you see some fluctuations there, but a lot less because you've got a lot of capability in there and they're maintaining it at a much tighter tolerance. So a couple things about active and reactive. This is power angle characteristics. We've talked about this a bunch of times. Now we're going to summarize it because now we have this concept of an infinite bus. So if our P is going out of this machine, this rotating machine, and heading into our infinite bus, this is acting as a generator. Okay. If our P is less than 0, so coming in from the infinite bus, it becomes a motor. So motor or generator action is just determined by the direction of P. So you can tell if it's a load or a source just by P. Q is much harder because it could be a load or a source. It just depends on the degree of excitation. So if I'm exporting Q to the grid, to the infinite bus, then that means that I'm overexcited. My Q is positive. It's in the overexcited condition. And again, Q can be to the right into the infinite bus, regardless of the direction of P. We talked about leading and lagging power factors a bunch of times in this class, so it can go plus or minus without any issue. If it's negative Q, so Q is going in the opposite direction of P, then that means it is going into the generator, into the motor. Sorry, let me back up. It's going in for the generator or it's going out for the motor because remember, the P is always positive. So if Q is positive or if Q is negative, well, if this is generating power, Q positive means it's out. Q negative means it's in. Whoops. If it's P of a motor, then Q positive, what direction is Q positive? In, very good. And Q negative is out in the opposite direction. So I can have a motor that actually can export reactive power to the grid. And in some of these old industrial power plants, not power plants, old mills, where you had something that was running at a constant load, instead of having a capacitor bank that would fix your power factor, you just buy a motor that you put, synchronous motor, that you'd put a voltage regulator package on it, and they would sit there and adjust its output to maintain whatever power factor you want. That's a much more elegant design for fixing power factor because of the cap bank, it's either all or nothing. So your power factor is whatever it needs to be. But if you're trying to maintain a specific power factor, which is ideal for the load, right? The company that is out there, they want to maintain, as little power to the utility as possible, reactive power. So they just do it to meet their demands. And so they'll sit there and they'll run at the bare minimum as much as they can. So you'll see those more and more. As I mentioned, synchronous condensers, those are becoming more and more common. And there's one that's going into New Hampshire, 50 MVA, to go ahead and basically just do that. It runs as a motor all the time, which means it spins with no load. And then it just outputs or inputs reactive power depending on what the grid needs. We talked a lot about the values of EF, which is your armature voltage, your terminal voltage, and then your angle, your torque angle. Let's take a look here. Hopefully this is legible. But what I see is my current here. I have IA prime, and IA double prime. What I'm doing here is you'll notice that my magnitude of EA is fixed. It's not changing, right? You can see that it's a fixed value. So what this means is that the excitation that I have is not changing. That magnitude that I see for EA, I'm not changing that at all. The only thing that I'm doing is I'm increasing the magnitude of current. So you can see that the angle is changing a little bit, but it's only changing a little bit because I have an inductor and a resistor over there. So all I'm doing by increasing or decreasing the magnitude of the current is I'm increasing or decreasing P. So I can take more power out of the machine, and I really don't affect the magnitude of the voltage that is seen in the machine, real power out of the machine. I might have to tweak it a little bit because you can see this angle is changing a tiny bit. But again, the reason why it's changing is because across my inductor, I'm getting some power loss there. But if that was small enough, all I have to do is set my excitation, that field current, to a certain value. And I keep doing this because that's what you do in industry. You have something called a pistol grip switch, and it looks like a pistol grip, I guess. And you increase or decrease your excitation. You can do it manually so that you can have a fixed value of voltage. And then the load, the real power demand, is increasing or decreases, and that's all based on the load, and you get that value. That's why you can see your power is increasing. Real power is increasing, not reactive power. But if you start to monkey with the power factor, now you're going to have to change these fairly significantly. So in a real world generator, you have two control systems. Control system number one is whatever the mechanical prime mover is driving it. If I have a steam turbine, I want to maintain whatever synchronous speed is, 1800 RPM. So I have a governor, that's called a governor, like a speed governor, right? Anybody, I don't know, I'm trying to think of like lawnmowers have governors on them, cars have carburetors and stuff, or golf carts have governors. So they maintain a certain speed?
They just limit.
Oh, they limit it. So, okay, I'm trying to think of something that would have a governor. Usually it's something that operates at a constant speed. So I'm thinking of like lawnmowers. Well, cruise control is kind of because, again, you're varying the speed. But when you crank your lawnmower, what do? It just runs at a speed and you go. Same thing with a snowblower, right? You can ramp up the speed, but once it's up to a certain speed, you don't mess with it anymore. Those are governors. That's why they call governors, because they're controlling the amount of fuel based on the speed. So if you load the thing down, you go over a big bunch of grass, the thing wants to slow down, so then it puts more fuel in it. Whereas when you don't have anything you're mowing, it lets less fuel. And same thing with a snowblower. That's the speed control, governor control. The other control system is the excitation control system, because I'm trying to maintain whatever terminal voltage on my generator. I want that to be at 480 volts or whatever voltage you have. And so it's going to adjust its excitation constantly. So that's called voltage regulator. So in every synchronous machine or synchronous generator that actually generates power, you need a governor and you need a voltage regulator. And the voltage regulator, usually, sometimes you hear it termed excitation system, but that's essentially what you have, two pieces of the pie. So here's a couple of things about our phasor diagrams. Again, phasor diagrams are really good to sort of show you what's happening. You can see that in my leading power factor, my voltage is always going to be at an angle of 0, whether it's leading or lagging, but my current will lead or lag. Then I have a voltage drop, IARA, that's the one across the resistor. Then I have an impedance, my synchronous reactance, I multiply it by IA, and then I end up with a magnitude here. For a lagging power factor, again, this is a generator, it's much, much longer. So I need way more excitation to be able to make that work than I do for the lagging power factor. This one also shows, and it's kind of hard to see, but you can actually see that your power output is pretty different too, because your torque angle is different. So you're also putting out a very different power here because of the leading and the lagging power factor. So if you wanted all things to be equal, if you wanted these to be the same, this would have to be something that is much, much shorter if you wanted to do that. So you can only do things, you have a limit on what you can actually accomplish. All right, let's do an example. 208. Let me just make sure that everybody can hear me. I thought it'd be muted. Yeah, and I'm recording. Okay. 208 volt, 45 kV. It's delta connected, not Y, but delta. 60 hertz synchronous machine has that same synchronous reactance we looked at on Tuesday. And we're going to ignore R sub A. We want to find the armature voltage, that's that EA, or the voltage that's determined from excitation. And we want to draw the phasor diagrams given the following loads. 12 kilowatts at 0.8 power factor, leading. And then 20 kilowatts at 0.8 power factor, both are leading. All right, so let's go ahead and draw the equivalent circuit. So I have a single phase representation. Everything we do in this class will be single phase representation, just makes the math a lot easier. So we have an internal voltage EA. We have our synchronous reactance, J1.04. And my output voltage has to be at 208 volts. So you'll see I have plus minus 208 volts at an angle of 0. Why is it 208? Shouldn't it be 208 divided by the square root of 3? Because it's delta connected, right? Line and phase voltage are the same in a delta circuit. So I cannot divide that by the square root of 3 and get the actual voltage across the single phase. I need to keep it at 208. Also, what's going on here? I'm dividing 12 kilowatts by 3. Is that valid? Delta? Yeah, so each load is responsible for 1/3 of the 12 kilowatts, correct? So if this is a single phase representation, I only want to show one phase of load, not 3 phases of load. So I have to convert that to a single phase equivalent by dividing by 3. So I've got my 4 kilowatts, and now I'm just trying to solve for S, right? This is determining that value of S. So I go 4 kilowatts divided by the power factor, which gives me S. And then I have the angle of 36.87. I put a positive 36.87 because I'm actually calculating the current. And since this is a leading power factor, I've got to go ahead and put the plus term in there for my current. And then I divide by 208 volts, which is my phase voltage, and my current going out of one phase of the generator. This is not going through the line. This is just going through one phase. Is 24.04 at an angle of 36.87. Once I have that, I can go ahead now and calculate what this voltage needs to be just by using KVL. Some of the voltage drops around a closed loop has got to be equal to 0. And so I go 208 at an angle of 0. That's my reference, plus J.104 multiplied by my current. And oops, I made a mistake here. My voltage is 194.03. Shouldn't it be greater than 208? I have a source. Have you ever built a circuit where your source voltage is less than your load voltage? That would indicate you're getting energy for free someplace, right? Or does it mean that? Capacitive? What does that mean?
Because it's a leading power factor. So your Q would be going in the opposite direction.
Yeah, Q is going in. So some of the magnetic field that I need for that, right, that V squared over X or I squared times X, some of the magnetic energy that I need for that reactor, or all the magnetic energy I should, is most likely going to come from the terminal connection. So I want, this is excess Q, right? I have too much Q in my system to be able to do anything with it. That's why my power factor is leading. So I want this generator to gobble up that extra Q that's on the grid. And how does it gobble it up? The voltage at the internal voltage has to be less than the terminal voltage because it's an underexcited machine. The voltage is less than the terminal voltage. And I can see that here. Look at the magnitude of VT relative to EA. Magnitude is less. But it still operates as a generator because my torque angle is positive. The angular difference between EA and VT is a positive number. It's around 6 degrees. And then my current doesn't really matter all that much other than to help, sort of show the voltage drops, is showing it over here. By the way, what is this right here? What vector is that? Anybody know?
So your loss over your XS.
It's JXS times IA. Right? If I rotate this 90 degrees, that's what that is. Because of the J term. So that's what we get there. 5 minutes. Part B is the 20 kilowatts, right? Everybody's looking at me funny. Remember there's 2 parts? Do you want me to leave the details up, or do you want me to leave what the questions are? There you go. Give you 1 more minute. All right, what'd you get? 120? I think it should be greater than, well, is it greater or is it that low? 242? It should be less than 208. All right, well, let's try it, what I did. And I actually got cute. Look at this. I made a MATLAB file that will help you. You can just specify whether it's leading or lagging. You just enter it in here. You could actually have MATLAB ask you a question. But here's your power, S. Here's your synchronous reactance, your power factor. And I said lead or lag. And then I have an if statement. You can actually see, as long as you text, and text with MATLAB, you can use apostrophes around it. So it does an exact match. But if the power factor type is lead, then it puts a -1 in here. Why does it put a -1, not a +1? Because of the conjugate. You see the S term here? S would be a -Q, right? It goes in the opposite direction for leading. So that's why it is equal to -1 and not +1. Where if it's lagging, it becomes +1. And then I solve for my S for a single phase. Notice the dividing it by 3, but the angle doesn't change. It's the power factor sign, right? And the power factor sign is just plus or minus 1. So I just added that in there to multiply times J times the inverse cosine of the power factor. Then my terminal voltage, it's 208, but it's delta. That's also the same thing as my phase voltage. My current, this is the current that is going out of the machine. This is per phase. So conjugate of single phase load divided by the terminal voltage. Then I like to just display what the current is, just in case you want to know what that is. Then I calculate my EA, then display it. And then I can also use this thing called compass, which will allow me to provide or present both EA and VT. You could actually also include IA, but like I said, it doesn't have as much information. So let's run it. And there you go. Hard to see, but this is the angle. Let's see if I can zoom in a little bit. This is EA, and this is VT. Notice the magnitudes much, much smaller there. Let's look at the data. So I have a current is 32, right, which makes sense because the went from 12 kilowatts to 20 kilowatts. But look at my magnitude for my voltage. It was it's now 189.8 or 0.9. So it's slightly increased from the 12 kilowatts because I have more current going out of the machine, right? It's at a higher value. So actually it went down a little bit. Why did it go down? Because there's more Q available, right? It's 20 kilowatts at a 0.8 power factor and 12 kilowatts. So it actually has more Q being supplied. Yes, sir.
Your EA finding got 189, right?
Yeah, at an angle of 8.07.
I got 166.
Anybody else get 189? I mean, you can take a look at the equations. I don't see any obvious mistakes here.
So can you talk about the equation again? Yeah, what example?
What equation?
Example.
In the slides?
Yeah, like, so I just have to change for the current, I just have to change.
You have to calculate this and put it in here. That's the only thing that changes, right? Because it's a generator that's designed to provide 208 volts. So that doesn't change. 20 kilowatts. Isn't that what I have right
I
here?
think you just get that current. 20 divided by 3. Yeah,
What current?
20 divided by 3 divided by 0.08 divided by 208. Yeah, that's, I didn't get that.
Oh, okay. So you're right. So I forgot to divide that by the power factor.
I was like, what am I?
So
Positive angle or negative?
the S is gonna be a negative angle.
You're,
See the power factor sign? I'm making a -1 here because it's a leading power factor. So S is, let's run it again. It's a leading power factor. So what do we know about the current?
is it just missing in the slide then? The negative? There should be negative in the slide as well.
Nope, it's positive current because the current leads the voltage. Right? I've already taken the conjugate in this equation. So you see the positive angle here? I've already conjugated it. That's why it's positive current here. Over here, I did the full Monty, right? You can see when I actually calculate I take the conjugate of I, so I didn't do it there. So let's see, I ran it again because I forgot to divide by power factor. Thank you. And now I get 186 at an angle of 10. And then let's look at compass. Not a huge change, right? It went from 189 to 186. The angle increased slightly, but you get the idea. Let's compare that just for giggles. Let's move over to lagging. So I just changed lag there. And I run it. Oh. Didn't like something. Huh. I'm not sure why it is burping at. It works fine when it's lead. I don't know. I have to, I thought this was debugged, but
There's space between your lag and your parentheses and that dip, that matter. At the end of lag.
it shouldn't make a difference here. I can certainly put it in
Wait, after the G.
right here. There's no space here though.
No.
Let me try doing it again and let's see. Arrays have incompatible sizes. Maybe they're supposed to be. Maybe they're supposed to have the same number of characters. Yeah. Gotta love MATLAB, right? It's so particular. I just had to make sure I had 4 characters. And then it works fine. But if you look over here, you'll see that, well, actually, let's do this. I'm just gonna do one more thing. Let's try it if I clear it every time. Does that make a difference? No. Okay. Doesn't seem to make a difference. So if I run it with lagging, now look at my voltage. I was at 186. Now I'm at 235. So if I go to my compass, look at the EA now, how much bigger it needs to be to provide excitation for its own system, as well as what the grid needs. So much bigger magnitude. But you'll notice the angle is still positive. It's a slightly different angle, but it's still positive. And that's what we want for a generator. So torque angle always has to be positive if it's a generator. All right, questions on that? Hopefully not too bad of a. I'll add this note here. That way it'll work, and I don't know why it didn't work this time, so. Okay, so last couple of things, then we'll finish up synchronous generators. So let's start with our equation for S, P plus JQ, which is VI conjugate. And we'll start off with our voltage being at an angle of 0. So that's what the VT plus J0 is going to be equal to. And then I'm going to go ahead and write my EF. What am I writing it in here? What form is this? Isn't that using Euler's identity to go from a number that is polar to rectangular? EF times the cosine of delta is the x-axis. J times EF sine delta is the y-axis. So all I did here was take EF, which you can see, it's kind of hard to see, which is a vector, and now I've converted it into its polar or rectangular coordinates. Now I'm going to have to solve for I, and I'm going to plug in all my values. So I have EF minus VT. No problem to combine the real parts. VT is all real, so I subtract the real parts from here. And then all I have is the imaginary part. Then I divide it by J x sub s. Don't include RA, it makes it easier. Multiply by 3 VT to get my actual power. So I put my 3 VT out front. And now I break up the real parts and the imaginary parts. You'll notice that this term over here, the J's cancel out. So this is actually the real part when I divide by the complex number. So that's why I have VTEF sine delta over XS. And then this is the imaginary part. This is the Q part of it. So P is equal to 3 VTEF sine delta divided by X sub S. And Q is equal to this term over here. Notice I took the J term out because Q is a scalar number. It doesn't have any J terms. It's just a number. Well, what does that tell me? That tells me something really important, because look at the power output of the machine. The real power output of the machine is determined by a couple things, right? It's determined by VT, EF, sine delta, X sub S. X sub S isn't changing. It's fixed. It's always going to be X sub S. VT and EF, you might get some changes in the EF, but remember, we're going to a fixed voltage because we're always trying to make sure the customer has whatever voltage they expect. So VT is not going to change. EF can change maybe up to plus or minus 10%. So you can get some changes in the power output by changing VT. And we saw that when we went from 12 kilowatts to 20 kilowatts, we saw that the angle changed slightly, but it was a small change. What is the biggest input or biggest effect on the power output? Sine delta. What is the sine of 0 equal to? Square root of 0 over 2. What is the sine of 90 equal to? 1. Square root of 4 over 2. So this can make our power be 0 or can make it be maximum. So if you remember what we talked about at the beginning of the class, how do you increase the power output of a generator? You have them spinning, you have the induced torque or the induced magnetic field. That's because the current's flowing out of the machine. That's going to give you a corresponding vector. That's when you have the 3-phase currents flowing in the stator, and they're going along and they're creating a magnetic field. Now we also have on the rotor, we have a magnetic field, and those two are going to have a gap between those two. And how do you increase the output power of the machine? You walk up to the controller, the governor, and you say, put more fuel into it. What that does is it momentarily increases the speed of the generator so that your angle starts to widen out a little bit. And it will stop once the angle is wide enough. So whatever value of steam you put in, because another way to say steam putting in is you're putting more mechanical power in. So as I increase this angle, it increases more electric power out. So by changing that torque angle, changes the amount of power that the machine can produce. And you can go all the way up and increase that angle until they're 90 degrees apart. Would you ever want to run that way? It might slip, but more often than not, if anything changes, if you try to increase the torque angle anymore, what ends up happening? You put out less power. Because when you're here, Can't get any more power out of it than that. So if you continue to try to increase the power angle, putting more steam into it, you actually decrease the electric power out. What is decreasing the electrical power out due to that machine that you're putting more steam in? It doesn't spin up momentarily or speed up momentarily. It continues to speed up until, as Barzilli said, you actually might slip a pole. And then you're constantly going to be bouncing poles around. So this is called my steady state stability limit. And that's the maximum you can go. You probably will operate a generator right about here. And interestingly enough, because it's an AC machine, it can operate as a generator or a motor. So you could switch it around and say, I'm going to put more mechanical load on the machine. I'm going to put a larger brake or something on the shaft to make it pull in more power until such time that I put so much that I'm beyond that 90 degrees, and then it actually slows down. Now I have too much load and a machine that slows down. So you're eventually going to lock up the machine. It's not going to be able to move. So, yes, sir.
What did you say that top one was, the SS limit?
Steady state limit. It's right here too. Steady state stability limit. That also applies for transmission lines and all that type of stuff. Yes, sir.
What would you want to be as close to that same limit as possible?
Good question. Why would I want it to be as close to the steady state limit as possible? Because in the real world, stuff is never perfect. So in the real world, you're running at, let's say, 85 degrees. And then all of a sudden, your neighbor who was screwing around on his generator trips his generator offline. So now you've got way more power demand than before. So all of a sudden, the torque angle has to increase until you've exceeded the limit. So by being over here, you've got margin. Safety. You've got margin. I don't know if we really call it safety, but remember the grid, the purpose of the grid is to provide customer power as reliably as possible. That's number one. Everybody who sits here and said, I want to make sure that the power is as cheap, as efficient as possible, that would not be the truth. Because if you want the cheapest power possible, I can sell you the cheapest power possible. But if you're okay without having power for 2-3 days at a time, then we have a deal. But that's why they have to maintain the trees. They have to cut all the trees down instead of waiting until stuff gets broken, then they got to go out and fix it. It costs more money to maintain your system to very high reliabilities. So we are willing to pay more for a reliable system, even though you complain about your electricity bill. I didn't hear anybody complain about last week when they had the AT&T cell phone problem. Anybody hear about that? I felt the pain. Cost me $2,000. My wife was going back to the airport on the day that went down, and she didn't have her GPS working because the cell towers were not working, and so she went in the wrong direction and missed the flight. So I had to book her on another flight one way. That day was $2,000 for 3 of them. So should I pay more for my cell phone bill? Better not, because I don't want to pay more than $200 or whatever I pay. But still cost me $2,000, so, or cost us $2,000. So anyway, electricity, we had a blip of power this morning. When I left my house at like 6:30. In the neighborhood, we all lost power. And it's like, oh, okay, what's going to happen? Well, we were fine, right? For an hour or 2 or even 3. But I'm like, okay, if it's after my 12:30 class, or 12 o'clock class, we still have no power. Now you could worry about the house pipes freezing. So then I was gonna have to go home and plug in a generator. So you can see the difference, right? I'm willing to tolerate a certain amount, but the AT&T one was no big deal until it hit my wallet. Whereas for the electricity, that was becoming a problem. 4 or 5 hours, everything in my refrigerator I have to throw away. The heat doesn't work. There's a bunch of different problems. So again, it's just becoming to the point where we need it, right? It's like water. I mean, we're committed to it. So I said on here 15 to 20. Some machines you can push them a little harder, but you want to have lots and lots of margin to go ahead and do that. And then this also shows you as you increase P, your Q is actually at a maximum when your torque angle is 0, but in reality, your generators can't do that. That's just dictated by these equations. But your Q cannot output more than when it's at 0. If you remember from our Northfield mountain curves, we actually saw what was called the capability curves. It was pretty flat like this, but then at some point, once it dropped below 0.9 or whatever, then it sort of cut off. So you have some real problems there. That is it for chapter 4 and synchronous machines. Now you can go out and you can parallel stuff and you can run generators. So when you're looking at a big generating facility, even if it's small, if we went to the hydroelectric facility that I don't know which one's closer. There's one over by almost downtown Orono, and there's one you can see from the bridge. But if you went there, you'd look, and the biggest thing that they have, or the most important thing they have, is a synchronous generator. Makes us power. Well, actually, doesn't make power, it converts power, right? You don't make power, you convert power. All right, questions? Somebody might have a question. Different question. Nope, did I lose the, okay, the class is still there. All right, I thought I lost the class, so. All right, any questions? All right, there's no questions. Have a great weekend. And I'll see you all on Monday for our next lab. Don't forget we have lab on Monday, right? All ready to go. So take care, everyone.
Thanks, Paul.
See ya.
See you tomorrow. See you Monday.